Welcome, everyone, to NTT R&D Forum 2025. Thank you so much for joining us. I'm Yagi from NTT's Market Planning and Analysis Department. My department gathers market needs and feeds them back to R&D to create businesses that don't yet exist. So today's quantum theme is a perfect fit for what we do. But first, I'd like to ask you all questions. Since you're here with us today, I'm sure you're all interested in quantum technology. Could those of you who know a bit about quantum raise your hands? Thank you. This field is gradually gaining attention, with articles appearing online regularly, so many of you have probably come across them. Now, one more question. How many are already using quantum in your business? Please raise your hands. I see a few hands here and there. That's excellent. This is still an area we need to continue exploring as we move forward. Which brings us to today's theme, Quantum meets IOWN, Social Change and the Future of Business. We'll have two 20-minute presentations followed by a 10-minute panel discussion. Now, let me invite our two speakers to the stage, Mr. Shirai, Mr. Yazane. First, we have Mr. Daisuke Shirai from NTT Network Innovation Laboratories, an executive research engineer at NTT Labs. He worked on video distribution and optical communication, then launched an optical quantum computing project in NTT's Research and Development Planning Department. Today, he continues to lead that project. Our other speaker is Mr. Yazane. He's a section manager at NTT Data Group's Technology and Innovation Headquarters. He's been engaged in developing systems that use mathematical models like optimization. He proposes projects in finance, public sectors, and other industries handling design and development work. 7 years ago, he launched a quantum computing commercialization team, which continues to this day. We'll start with Mr. Shirai, who will present from a vision perspective. Mr. Shirai, the floor is yours.
Thank you for joining us at R&D Forum 2025. As just introduced, I'm Shirai from NTT Network Innovation Laboratories. Our lab manages R&D across both hardware and software for optical quantum computing. I'm excited to share this today. Let me start by sharing some highlights from our press announcement on November 18th. Some of you may have already seen this on the news, so I'll keep this brief. The optical quantum computer we're developing was conceived by Professor Akira Furusawa at the University of Tokyo. OptQC, a startup founded primarily by graduates from his lab, has partnered with NTT to achieve universal large-scale computation with a 1 million qubit optical quantum computer by 2030. Those are the details of the recent announcement. OptQC's CEO, Mr. Takase, will be speaking this afternoon, so I'll leave the technical details of how optical quantum computers work to him. I'll focus on the overview and our vision within the IOWN initiative. First, we have a video about the challenge of optical quantum computers. Let's take a look.
最新のコンピュータや AI 技術でも解決が難しい問題に対し、量子コンピュータの期待が高まっています。量子コンピュータの研究は近年急速に進展し、産業化の波が押し寄せています。市場予測では2030年代には数兆円規模に成長。期待はかつてないほど高まっています。量子コンピュータには超電導、中性原子、光など様々な方式があります。NTT は光通信技術から生まれた光量子方式に挑戦。光の特性を生かすことで高速・省電力で圧倒的なスケーラビリティを実現。通信との親和性も高く、未来のネットワークとつながる力を持っています。私たちは光の力で量子計算を次のステージへ導きます。それはエネルギー効率を極限まで高めた 持続可能な社会の新しい計算基盤です。産学連携による技術開発の加速と光量子の開発コミュニティの拡大を図り、2030年に汎用的大規模計算が可能な光量子コンピュータの実現を目指します。将来はIOWNのコンピューティング基盤の上で地球規模の量子コンピューティングを可能にします。未来は光とともに。
Next, let's talk about why quantum computers can solve problems that even the most advanced computers struggle with. I'll explain this briefly. First, here's a video regarding qubit superposition.
箱に入ったオセロは開けるまで表か裏か分かりませんが、状態はすでに決まっています。一方、量子は表でも裏でもあるという2つの可能性が同時に存在できます。1つの量子ビットで2通り、2つで4通りと指数関数的に計算できる通り数は増え、わずか80量子ビットで星の総数以上の可能性を並列計算できるようになります。この並列性が無数の可能性を一度に解き明かす光量子計算の力です。
So, using this property of qubit superposition is the key difference. Next, let me compare classical computing using traditional 1 or 0 bits with quantum computing. This is a very simplified explanation, but I'll walk you through the differences. For example, suppose we need to find one correct answer from 2 to the power of 80 combinations, more than the number of stars. A classical computer would essentially check each combination one by one, as shown here, verifying whether each one is correct. Ultimately, it would need to check all 2 to the 80th power combinations through brute force. Of course, if you're lucky and find it early, you can stop there. But typically, as shown here, it would take about 20,000 years. In contrast, a quantum computer uses the property of qubit superposition I just explained. For instance, with 80 qubits, we can spread out all 2 to the 80th power combinations at once, and they all exist simultaneously. Each possibility is represented as a wave with a certain probability. Quantum computation then operates on these probability distributions through interference, canceling out impossible solutions all at once, while amplifying the likely solutions. That's how it works. By repeating this several times until we get a clear answer, not by checking one by one, but by repeating these wave superpositions, we can reach the solution much faster. Only the correct answer stands out with high probability, appearing as a sharp peak. With this approach, what would take 20,000 years classically can be solved in just a few days. As you can see, quantum computers work using a completely different calculation method, and research is advancing across multiple quantum computing approaches. Superconducting systems are the most mature, but in recent years, neutral atom and ion trap methods have seen rapid growth. These approaches will be compared in detail during the upcoming talks, so I'll just cover the essentials here. Unlike other methods that require physical placement of qubits, optical quantum computing sends qubits through optical fiber as light. So the critical advantage is that we can scale the system just by extending the fiber. We also don't need cryogenic cooling or vacuum chambers. No large-scale control infrastructure required, which means we can keep power consumption to a minimum. That's our approach. Now, when I say a few hundred watts, we're not quite there yet. But that's the target we're working toward. I'll come back to that shortly. Next, I'd like to discuss the key technologies behind optical quantum computers. Here you can see the system architecture of our optical quantum computer. In this system, we use light to create the qubits that form the basis of computation. For the quantum light source and for observing and controlling the quantum light, we use a device known as an optical parametric amplifier, abbreviated as OPA. This is NTT-developed technology. In optical communications, it's used to amplify optical signals with low noise and transmit them over long distances. In IOWN's APN network, we use end-to-end wavelength paths, and OPAs can convert the wavelength of multiple paths simultaneously. Dr. Umeki, our senior distinguished researcher, will explain this in detail this afternoon. But essentially, when we input a communication wavelength laser, it can tightly compress quantum noise. This allows us to create light pulses that serve as the foundation for quantum computation. Compressing quantum noise is called squeezing, and the more tightly you squeeze, the fewer errors you have and the more robust the quantum state, meaning you can create higher quality qubits. We've currently achieved 8 decibels of squeezing, which is world-leading performance. This breakthrough has finally enabled practical quantum computation using light in recent years. OPAs can be used on the source side as well as the receiving side as amplification devices. Quantum light, that is, light with entanglement, cannot be amplified in principle. However, when we observe quantum light and convert it to classical information, we extract that signal, and at that point, once we've set the measurement axis, we can amplify it. This means that even weak quantum light can be properly received and measured. Improving precision on both the transmitter and receiver sides is critically important. Now let me touch on the history of NTT's optical technology R&D, the foundation for both IOWN and optical quantum computing. This graph shows how transmission capacity per fiber has increased over time. Initially, we communicated by simply turning lasers on and off, but with wavelength division multiplexing, WDM, and optical amplification technology, capacity grew dramatically. After 2000, digital coherent technology emerged, which allows precise digital control of optical wave properties. This enabled not only higher capacity, but also extremely high-quality optical measurement and control. Today, as you can see on the right, we can integrate these complex functions onto fingertip-sized chips. These decades of accumulated expertise in freely manipulating and precisely controlling optical waves, plus high-density integration technology, are now driving the evolution of optical quantum computers. Next, let's discuss why IOWN technology is expected to drive global power savings. Why is light more power efficient than electricity? Let me explain briefly. The graph on the left shows circuit power consumption, where blue represents electrical circuits and yellow represents optical circuits. When electrical signals pass through conductors like wires, there's unavoidable electrical resistance like friction, which generates heat. The faster the operation, the more heat is generated, consuming more energy. What's worse is that this heat then needs to be cooled, requiring even more electricity. On the other hand, the yellow line represents optical circuits, which don't generate heat when passing through fiber. For signal transmission alone, optical is dramatically more power efficient. Of course, this includes laser power consumption, but it's still far more efficient than electrical circuits. The graph on the right shows transmission distance versus capacity. Optical communications have traditionally been used for long-distance transmission, like undersea cables. Recently, electrical heat generation has become a critical issue. So in the circled area at the upper left, these short-distance connections are shifting to optical. For example, in data centers, between racks, between machines, we're seeing a shift to optical. And even shorter distances, board to board, chip to chip, are going optical. Now, optical wiring does present some challenges. Electrical connections work as long as they're physically connected, but with optics, the optical axis must be precisely aligned, or signals won't transmit. implementation becomes extremely challenging. But overcoming these kinds of technical challenges, that's where NTT's technology comes in. At the start, the video highlighted 3 key advantages of optical quantum computing: compact footprint, high speed, and low power consumption. But these advantages don't come automatically. So when we set these as our targets, what challenges do we face? These are the challenges we need to address. Let's look at how we tackle each one. First, the scaling barrier. We need quantum light to reach its destination without degradation. Earlier I mentioned the OPA, the optical parametric amplifier, which incorporates a PPLN waveguide. This lets us generate quantum light with very high squeezing levels. Currently, we're using time division multiplexing, packing multiple qubits along the time axis. But we can also use wavelength division multiplexing or space division multiplexing. There are many different multiplexing approaches available. The key here is our experience with high-capacity, low-loss optical fiber technology. Next, speed. We're aiming to run the system on an optical clock. We're targeting terahertz-level operation. To achieve that, we currently rely on several electronic circuits, but we're working to design and implement those computation and measurement functions as optical circuits instead. And we have the technology to make that happen. Next, the miniaturization challenge. Right now, we arrange mirrors and lenses in free space, firing lasers through them to generate quantum entanglement. But with co-packaging technology, we can integrate both optical and electronic components into a unified package. This enables dramatic miniaturization. And at the same time, we can achieve major gains in power efficiency. When we implement these optical circuits in real-world systems, co-packaging will be the key enabling technology. Finally, the power efficiency challenge. How do we minimize the electrical components? Lasers, modulators, and other functions needed for optical signal transmission. We can implement all of these as integrated chips. Technologies like silicon photonics and membrane photonics, these will be critical. Here we have the gate-based quantum computer currently operating at RDF2025, the world's first 101-qubit machine. It sits on a large optical table designed to absorb vibrations. On that table, we arrange mirrors, lenses, and other components to build the circuits for entanglement generation and quantum teleportation. By 2030, we'll boost the quantum light source performance and clock speed to reach 1 million qubits. Simultaneously, we'll integrate these circuits using the optical technologies I mentioned earlier, working toward a rack-scale optical quantum computer like the one shown on the right. The 1 million qubit target is 2030, but achieving the rack form factor is more challenging. We're targeting sometime in the 2030s for that. But once we achieve this, the impact will be enormous. We'll be able to deploy quantum computers across a wide range of data centers. That will mark the beginning of true practical quantum computing, the quantum era. That's our vision. So assuming optical quantum computers become a reality, how will we actually use them? Let me talk a bit about that. Optical quantum computers are fast at quantum computation itself, but ultimately, we're aiming to run them on optical clocks, enabling extremely high-speed processing. To fully leverage this speed, we need connections to high-speed networks and data transfer infrastructure. Now, quantum computers won't replace all computers in the world. They're especially good at problems like finding the right answer from massive combinations, as I mentioned earlier. But for tasks like text processing or media processing, there's no real benefit to using quantum computation, so traditional computers will remain. To solve real-world problems with quantum computing, including human interfaces, we need classical computing resources like CPUs, GPUs, and storage. This is where IOWN's optical computing infrastructure comes in, allowing us to transfer data from resource to resource at ultra-high speeds via optical communication. As a quantum computing accelerator, we believe this will maximize its potential. This is a network-native optical quantum accelerator, designed from the ground up for network deployment. That's what we're building. To fully leverage this technology, we'll need hybrid quantum computing, combining CPUs, GPUs, and quantum processors. We're actively exploring that approach as well. So, how will optical quantum computers actually be used? What real value will they bring? By around 2027, we'll optimize large-scale communications, transportation, energy distribution, all dynamically, based on real-time conditions. At this stage, we can't definitively say quantum will outperform classical computers, but still, we believe we can reduce tasks that take days down to just minutes. By 2030, with 1 million qubits, we'll have fault-tolerant capability, making it possible to run large-scale calculations requiring many sequential steps. On a much larger scale, the 8 billion people on Earth depend on fertilizers that help crops grow. To produce these fertilizers, you need ammonia. To make ammonia today, we use the Haber-Bosch process. This method creates ammonia from nitrogen in the air. Quantum computing could help us fully understand this chemical process. Because the Haber-Bosch process currently consumes several % of the world's total energy. If we could solve this problem, if we could fundamentally transform this process, that achievement would be worthy of a Nobel Prize. That's the kind of impact we're talking about. Problems that would take trillions of years, orders of magnitude beyond the universe's age, could be solved in 4 days. We're aiming for 100 million qubits. At that scale, we could develop new drugs tailored to each individual's genetic information. The time it takes to calculate that approaches infinity, 2 to the power of tens of thousands, but we could reduce that to around 10 days. At that point, quantum computing will truly transform the world, bringing about fundamental social transformation. Here's our roadmap. As I mentioned, by 2030, we're aiming to achieve a fault-tolerant, universal, large-scale optical quantum computer. And simultaneously, using software error mitigation along with advances in hardware, we aim to achieve early practical implementation. Through highly integrated optical circuits, as shown here, we're aiming for rack-scale systems. Our ultimate goal is to create computing infrastructure for a sustainable society. We'll also expand our development community, and from 2027, we'll begin demonstrating and validating use cases. By 2030, we aim to be the first to deploy optical quantum applications. Finally, looking toward the ultimate future, this is still quite far ahead, but we're also researching quantum communication, transmitting quantum information over optical fiber. With this capability, a global-scale optical quantum computer becomes feasible. Scaling out our quantum computing power would enable truly global-scale optical quantum computation. It may sound like a dream, but we have quantum sensors. If we could capture quantum information from the real world and send it directly over a network, then compute it directly on optical quantum computers, it's hard to say exactly what would be possible. But we could potentially simulate the real world with quantum mechanical precision. What kind of world that would create is beyond imagination, but it represents one ultimate vision we're striving toward. That concludes my presentation. Thank you for your attention.
Thank you, Mr. Shirai. You covered a lot, from quantum basics to the full potential of optical quantum computing. Now let's turn to the business applications, how to actually put this technology to work. Mr. Yazane from NTT Data Group will take us through that. Mr. Yazane, the floor is yours.
Thank you. I'm Yazane from NTT Data Group, and I'd like to share our perspective on leveraging quantum computers from a business standpoint. Let me start by taking a step back from business specifics and looking at the broader landscape. You've probably noticed the term quantum computer appearing more frequently across various media outlets. When we break down the rising excitement and expectations, we can identify 4 key drivers. First, as Mr. Shirai mentioned in his presentation, technological progress is obviously the biggest factor. This has led to numerous milestones being achieved. We're seeing proposals for achieving quantum advantage and quantum supremacy. And to make these practical, we need advances in managing noise for more stable, reliable operations. Progress is happening across all these fronts. That's clear. But naturally, the key question is how we apply the technology. From an industry standpoint, we're seeing very active exploration of use cases, which I think is a defining feature of this field. Chemistry and finance are commonly cited as early areas for quantum advantage. But research isn't confined to those domains. The strengths we identify in those early use cases are actively being adapted and deployed across other fields. That's the current situation. So, applied research is progressing across a very wide range of sectors. This technological and industrial momentum is being further accelerated by policy support that's being strongly promoted. And not just in Japan, government investment globally is increasing. More than increasing, I would say it's surging. Some regions have seen investment surpass $10 billion US, levels that aren't just on par with other tech fields, but among the highest investment tiers, driving fierce competition in development. Industry, government, and academia are all actively mobilized in this space. These efforts aren't happening in isolation. They're forming a robust economic ecosystem. Now, full monetization and profitability may take a bit more time. But as we saw at the start, when we asked who's using quantum, several hands went up. We're seeing gradual deployment in real business settings, and forward-looking initiatives that anticipate this trajectory are already well underway. From every perspective, expectations are running very high. So why are quantum computers attracting all this attention? I believe there are 2 main factors. First, on the left, we see HPC, high-performance computing. Demand in this space is rapidly expanding. That's undeniable. I'm sure this immediately comes to mind. The surge in AI demand has been tremendous. Chat-based AI, large language models, are now widely used by the general public. They've become completely commonplace. And now the competition centers on how to integrate it into workflows. Usage frequency is definitely climbing, and at the same time, the compute required per AI request is growing as well. All the while, AI versions keep advancing. These systems are clearly getting smarter, noticeably so. So the computational workload on the back end is growing correspondingly. And the competition per query is increasing in parallel. Plus, the scenarios we use these queries are expanding as well. Both frequency and quality are on the rise. So the computational resources demanded on the back end are surging. That's the situation we are in. Now, AI is just one example of where IT is deployed, and while AI's growth is certainly significant, In other areas too, the expansion of digital transformation means ICT infrastructure is now powering the back end of diverse business operations. So as DX accelerates, more opportunities emerge for IT systems to play active roles, and the data collected from these systems is also expanding. Previously, many processes were handled manually or analog, leaving no digital footprint or logs behind. But with accelerating DX, the data we can collect is becoming richer and more granular. Naturally, that's driving growing interest in how to leverage that data. As a result, demand is rising to analyze and utilize ever larger data sets, and to feed those insights immediately back into business operations, requiring high-speed computation. We believe this is where demand is heading. As shown on the left, increasingly convenient and fine-grained ICT services are being adopted at an accelerating pace. But the question is, are computing technologies keeping pace with this demand? I believe there are several challenges. First, existing architectures. The kind of computers you all have in front of you, these systems, as Mr. Shirai mentioned earlier, are often called classical computers. The existing architecture of these machines relies on processors called CPUs and GPUs for computation. The computational efficiency of these processors has been steadily improving year over year, following Moore's law, doubling at regular intervals. But the pace of this evolution depends on how much we can miniaturize semiconductor chips, making them smaller and smaller to achieve faster computation. That's the technological direction we've been following. But when you think about it, miniaturization has limits. Ultimately, even as we go from millimeters to microns to nanometers, and this may sound extreme, you can't go smaller than atoms and molecules. So there's clearly a fundamental limit. That means simply extending existing architectures won't be able to meet AI demand indefinitely. That risk is very real. And this isn't limited to IT. With carbon neutrality becoming a global imperative, IT infrastructure accounts for a significant amount of CO2 emissions. So naturally, we need to consider how to build more efficient and sustainable ICT infrastructure. This is one of the missions we believe the NTT Group must fulfill. Given this situation, we can't simply extend existing computer technology. We need fundamentally innovative technology. I think you can understand this need, and quantum computers are a candidate technology to meet this challenge. Quantum computers offer the potential for large-scale, high-speed computing with low power consumption, covering all these requirements. This is why quantum computers are attracting so much attention. Apologies for this busy slide, but as I just mentioned, quantum computers actually encompass many different approaches. As mentioned in the previous session, there are various methods like superconducting, neutral atom, and optical quantum. Take a look at the right side of this diagram, the section labeled Quantum Computer Gate-Based. We'll start there. This is the quantum computer domain that most people imagine, computing devices that leverage quantum properties. These quantum properties can be realized with various materials, whether built with superconducting circuits, neutral atoms, or light. Various approaches are being explored. Naturally, all of these methods still face technical challenges, and we can't immediately build devices that can handle any computation perfectly. We're not there yet, but we're making steady progress. For business preparedness, rather than using actual devices, companies are experimenting with simulators. These gate-based quantum computers are capable of general-purpose computation. To realize this general-purpose computing, we need larger-scale qubits, quantum bits, as we call them in quantum computing. We need to scale these qubits and ensure they can operate stably. This is the heart of the current technology development race. Now let me turn to the left side of the graph. Ising machines. I've labeled these as gate-based quantum computers, but there are non-gate-based types as well that leverage quantum properties for computing. You may have heard about this in the news, but there's a technology called quantum annealing. This was spun out of quantum computer R&D and specializes in combinatorial optimization, a specific class of mathematical problems. You could say it's limited to that problem, but by taking this specialized approach, we can scale the hardware larger than the gate-based systems on the right. Focusing on this feasibility advantage, quantum annealing has reached commercialization ahead of gate-based systems. That's where this technology stands today. Quantum annealing also has simulators and implementations beyond superconducting, like coherent Ising machines and others. This family of machines specializes in the Ising model, a mathematical problem with combinatorial optimization, which is why they're called Ising machines, machines that solve the Ising model. The term quantum computer sometimes refers only to the gate-based systems on the right, and sometimes it includes the specialized systems on the left, too. The usage varies depending on the source, so being aware of this distinction will make it easier to navigate various materials. The right side represents general-purpose quantum computers, the left specialized machines. NTT's optical quantum computer, which we just discussed, sits on the right side, aiming to achieve larger qubit counts and reach practical applications sooner. That's how this technology fits into the landscape. Looking more broadly, quantum computing is expected to transform various industries. I've highlighted 6 industries with particularly high expectations. Let me start from the top right. The chemical and pharmaceutical industries are expected to adopt quantum computing relatively early. This is a bit simplified, but these fields involve calculations at the atomic and molecular level. At this microscopic level, behavior follows quantum physics, not the classical physics of our everyday lives. For example, objects can pass through each other with a certain probability. Things that seem impossible in daily life can actually occur at the quantum level. When we want to calculate quantum physics phenomena for chemistry and drug discovery, we currently use classical computers to handle these calculations. But naturally, using quantum mechanical computers would be far more efficient. So there's excellent compatibility here, and chemistry and drug discovery are expected to see use cases emerge relatively soon. Next are the top row use cases, finance, as well as AI and machine learning. These are expected to see significant activity. As I mentioned earlier, AI has extremely high demand, while finance can achieve faster, more precise calculations, meaning earlier return on investment. So both fields are seeing very active proof-of-concept work. Then, transportation and manufacturing on the lower left. These rely heavily on Ising machine calculations, specifically mathematical optimization and combinatorial optimization. These calculations are used extensively. In transportation and logistics, for example, an obvious application is optimal route planning, a classic optimization problem. Now, whether quantum computers actually help here is debated, but these fields align closely with mathematical optimization, so applied research is gradually getting underway in both transportation and manufacturing. Things like optimizing factory production lines and process control. There's a lot of R&D currently happening. Now, the lower right, security, is somewhat different. Once quantum computers achieve extremely fast calculation speeds, the encryption that underpins all our current security systems may be compromised. Encryption relies on problems that would take supercomputers tens of thousands of years to solve, which is why it's considered secure. If that foundation crumbles, we'll need to fundamentally rethink our approach to security. This is what we call post-quantum cryptography, encryption methods that can withstand quantum computing attacks. This is especially critical for industries handling sensitive data, where standardization and implementation are already being pioneered. At our company, for instance, the financial sector is well ahead in addressing quantum security risks. Many organizations are uncertain about what measures to take and when, so we offer support with security roadmaps to help navigate these challenges. It's an area of high interest. So, we have multiple industries, multiple types of quantum computers, and multiple use cases. I realize I've painted quite a complex picture. But the key is, what time frame are you looking at, and what impact are you hoping to achieve? It's crucial to think these through carefully. As I mentioned, different quantum computer types have very different maturity levels right now. So if you're taking a short-term view, asking what's usable today is absolutely essential. But looking much further out, once we have large-scale, stable quantum computers, entirely new business models may become possible. You can explore from that angle as well, building a pathway from near-term actions to long-term goals. Thinking about that continuity is really important. We call this our quantum journey process. For organizations tackling these challenges, we explore what cutting-edge technologies exist at each layer. We identify the most prominent technologies, including those from startups, introduce them to our clients, and map out pathways to quantum advantage. We provide this kind of consulting. And within the NTT Group, we're responsible for these solution offerings. We work with a diverse range of clients, helping them navigate the shift toward a quantum ICT era and determining the optimal services for their needs. As shown on the right, we maintain strong relationships with clients across diverse sectors, and we leverage those connections while gathering insights from clients globally to continuously explore these opportunities. Zooming out a bit, within NTT Data, we have an innovation center that works on advanced technologies beyond just quantum computers, exploring how to apply cutting-edge innovations in collaboration with our clients, especially global clients. For example, if a new quantum computer use case emerges in Germany with a promising idea, we can deploy it in Japan, or bring new technology from North America and see if it can work in Asia. This cross-border approach is one of our key strengths. Our quantum computing verification services aren't limited to NTT hardware. There's intense competition in hardware development across the board, and we're not tied to any particular hardware. Each machine has very different strengths and weaknesses, with varying maturity levels. So, NTT Data's approach is to match the most suitable hardware to each client's specific problem, or recommend the right hardware based on their timeline. We take a consultative stance, helping organizations figure out how to use quantum computers through verification and testing. Let me briefly touch on 3 use cases. The first is optimizing glass cutting operations. Marked short on the right, this was a test of what performance current quantum computers can actually deliver. We ran this with AGC. In conventional glass cutting, you punch out shapes like cookie cutters on a sheet, which leaves waste material. The goal is to minimize that waste. We compared the precision of conventional methods against quantum annealing and simulators. This case study examined those performance differences. Next, moving beyond what today's computers can do, we're exploring what new businesses might emerge if quantum computers become available. One example is scent reconstruction. We've shared this project through news releases and other channels, but we're partnering with Komi Hakko, an Osaka University spin-off that specializes in digitally expressing scents. The field of scent still relies heavily on analog processes, but by digitizing them, we could create metaverse spaces with scent, not just sight and sound. Imagine sharing scents in a virtual environment. However, current scent data is extremely vast and complex, making it difficult to determine in real time which scent to emit or detect which scents are present, as the computation is extremely heavy. In fact, Komi Hakko was taking up to a week just to compute a single scent. We thought our computing power and technical expertise might be able to help with this, so we're jointly developing a platform for scent analysis. Imagining what the world might look like once quantum computers become a reality and actively exploring these possibilities are both important. The final example is from a BMW competition where we partnered with startups. The automotive testing process is extremely complex, involving questions like which parts failed or passed, and how to minimize the number of vehicles destroyed in testing. We compared this testing process using current methods, today's quantum computers, and a future state with fully error-free quantum computers. We looked at how to leverage each one and mapped out the performance potential and roadmap for continuous progress. This became our quantum computer adoption proposal, and we actually took first place in our division with it. This case really illustrates how thinking through short, mid, and long-term approaches is critical when planning your response. Let me touch on one more thing. Use cases like these don't just emerge on their own. We provide guidelines on how to apply quantum computing, testing environments where you can experiment with actual calculations, and answers to key questions like, what level of quantum computer do we need to achieve our objectives? What problems can quantum computers of various scales solve? We've developed resource estimation technology and actively share the information needed to explore these use cases. This is a very active area for us. Finally, beyond just use cases, we're also confident in our ability to provide the data center infrastructure to run these computations. As the world's third-largest data center operator, this is a real strength for NTT Data. Ultimately, from applications all the way to computing infrastructure, we aim to integrate quantum computing technology across our complete end-to-end offering. Finally, as I've mentioned, quantum computers for business is still in a transitional phase. Many say we're only at station 1 or 2 on this climb. While NTT has set a target for 2030, we believe the field will accelerate rapidly in the coming years. To make that happen, we need more than just technical progress. We need talent development, ecosystem building, partnerships with many organizations, and clarity on which social challenges to tackle and how. The entire NTT Group is committed to advancing technology and business together as two wheels driving progress. Thank you for listening.
Mr. Yazane, thank you. We're now preparing for the panel discussion. We've covered practical applications, business scenarios, and case studies, which were all very informative. I have a few questions prepared for the panel. We have just over 7 minutes remaining, so let's move on to the panel discussion. Thank you. Please have a seat. Let's start with our first topic. First, most of us will probably use quantum in the future, but in exactly what ways? You both mentioned hybrid systems combining classical and quantum computing, and when I looked into that, it seems quantum computers have areas where they excel and areas where they struggle. Mr. Shirai, what are quantum computers good and not so good at?
As I mentioned briefly in my presentation, quantum computers excel at finding solutions from massive combinations of possibilities. But when it comes to processing text or media, classical computers are still better suited for those tasks. So classical computers won't disappear. Beyond massive combinatorial problems, as Mr. Yazane mentioned, quantum behavior like molecular motion or atomic interactions, these are things we want to simulate. And it makes more sense to compute them in the quantum domain. Those will probably be the initial target applications. That's what I see.
So classical computers will continue to play a role. Given that, how should we approach using quantum computers? Mr. Yazane, do you have any thoughts on this?
Thank you. From a user's perspective, to put it bluntly, I think it's important to just dive in without worrying too much. That's really key. As Mr. Shirai just mentioned, there are strengths and weaknesses, but we can use them in a hybrid way. If a task is well suited for quantum computers, you route it to quantum. If classical computers are better, you route it there. This kind of routing happens at the middleware layer, and research is already underway on this. So even if something can't be done today, if it could be done in the future, think about how it might create value and keep trying. That's what's important. My message is, don't overthink it.
That's wonderful to hear. If we had to worry about whether quantum is the right fit for each task, we'd never use it. But you're saying we don't need to worry about that. So we can use it freely. Now, the real question is, what can we use it for? We've talked about massive computation, so let's move to the next topic. I think what everyone here is most interested in is AI. We can't ignore that topic. AI is essential in business today, so how will quantum computing change this? Will it enhance AI, or are they separate things? I'd like to explore this a bit. Mr. Yazane, let me start with you. When we think about business applications, is there real excitement around this combination of quantum computing and AI? I'd love to hear your thoughts on this.
I think it's very significant. As I mentioned at the start of my presentation, AI is being adopted across more and more domains. And at the same time, the more users we have, the more we're also focusing on what current AI cannot do. And addressing these limitations through improved computing infrastructure, even if it's only in certain areas, I think expectations are quite high. Demand is definitely growing. I can feel it.
I think many of you share that sense, and people on the business front lines like Mr. Yazane clearly have high expectations as well. So will quantum computers actually help AI evolve? And if they do, in what ways? Mr. Shirai, what do you think?
Research on AI using quantum computing doesn't have a very long history yet, though there are many different approaches. Neural networks are widely used today, and of course quantum neural networks are being researched as well. But as I explained earlier, there's this principle of superposition. And fundamentally, neural networks take input data, produce output, and train by measuring deviation from the correct answer, making corrections iteratively. But because of the superposition principle, this becomes extremely difficult. So while various research is being done, the truth is we haven't found a definitive solution yet. However, superposition allows us to hold multiple possibilities simultaneously, which gives us a kind of parallelism, so expectations remain high. Many researchers are certainly trying, but we don't have a breakthrough yet. That's one side of it. But beyond directly implementing neural networks with quantum computing, even for current neural networks, quantum computing can be used for simulations, like drug discovery, for instance. We can generate training data and ground truth using quantum computation. So we can teach current neural networks about the quantum world, training them on that data. That approach certainly exists. And I also think neural networks could use quantum computing as a resource, actively leveraging what only the quantum world can do. Neural networks, or in other words, today's AI, classical AI, could evolve. So I think both of these approaches are viable.
In that sense, this field is still developing. So for us, it's about staying current with the latest developments and keeping our excitement alive as we explore what kinds of business applications might be possible. And naturally, at events like this R&D forum, we'll continue to present the latest research trends. So I hope all of you will keep following quantum forums like this one. We're running short on time, so let's move to our final topic, which is also the theme of this session. This might be the trickier one. Quantum meets IOWN. Both are connected by the keyword optics, which is starting to tie them together. But I think most of us only have a rough sense of how. Maybe even our panel feels the same way. So I'd like to hear from both of you, including your expectations. Just a few words from each. Let's start with Mr. Yazane. Quantum meets IOWN, social change and the future of business. Please share your vision with us.
I have high expectations. IOWN isn't just about computing. It encompasses communication as well, and that's the real key. Even with classical computers, as parallel and distributed processing technology matured, it led to the big data boom. Looking at that history, quantum computers will start by scaling qubits within a single machine. Then, we'll connect multiple systems to achieve even greater scale. As mentioned in Mr. Shirai's presentation, when we reach that vision, the scale will grow even larger, and we'll be able to do so much more. That's why I'm so excited about this.
Thank you. So connection is one of the key concepts. Mr. Shirai, I believe this will be the closing remarks for this technical seminar. What are your thoughts?
I may need more than a few words. As I explained earlier, the technology that gave birth to IOWN is connected to quantum computing. And what I'm most excited about is speed. We're even considering operating at optical clock speeds, which could create a computer with extraordinary computing power. That's the possibility. And with an extremely fast computer like that, we need to feed it massive amounts of data at incredibly high speeds and solve computations rapidly. That's where IOWN's optical computing comes in. Its goal is to transmit data as quickly as possible from one resource to another. When you combine these two, we might be able to solve problems at astonishing speeds. Finally, and I really don't know when this might happen, this could be quite far in the future, but imagine if we develop quantum sensors that can transmit quantum states from the real world directly. Right now, we're converting everything measured into classical data and then trying to solve it with quantum computing. But if we could bring in the quantum world directly, we could simulate the real world exactly as it is. I really think that could be possible. I don't know how many years it will take, but it would be truly exciting to see that happen in my lifetime.
Thank you. In that world, we could solve many issues that remain unsolved today, like understanding COVID transmission patterns and solving problems like that. NTT Group will continue advancing optical technology, quantum technology, and IOWN. We'll keep pushing forward with research and development and work toward commercialization. Our goal is to realize a sustainable society, so please continue to follow the R&D forum in the years ahead. We appreciate your attention. That concludes this session. Thank you very much for participating today.